All right, on this lovely day, we're going to talk about something that our dear friend Euclid, yes, Euclid, you don't have to write this down, Euclid, who is pretty much the founder of geometry from 2,400 years ago, in volume 2, or his book 2, proposition 12, he actually talks about the law of cosines. He didn't call it that, and if we were to read it, it would seem like something completely archaic, but we're going to talk about the law of cosines, and this is very uncomplex. So in a situation of side angle side or side 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 in a triangle, we're going to know and use something called the law of cosines to find missing parts, particularly missing angle measures and side measures. So our super secret distance formula, of course, we usually call D. We subtract the x's. We square that. We add that to the difference of the y's. We square that, and we take the square root of the whole thing. Now to find the exact distance between these 2 points, here, again, all we do is pretty much just go x to x, so we subtract that. So 2 minus radical 3 squared plus 0 minus 1 squared. Keep the radical around the whole thing. Notice I tend to draw my radical after so that it fits, and then put the D there. So we don't distribute this, rather it's FOIL, so we get 4 minus 4 radical 3 plus 3 plus 1, all square root. And we combine our like terms. 4 plus 3 plus 1 gives me 8. So 8 minus 4 radical 3, and the whole thing is being radicalized. And that's my answer. So when we plug it into our calculator, we get approximately 1.035. That's my thousandths. We don't have any units, so we just leave it as such. Now let's go ahead and jump into the content of beautiful law of cosines. It is a plural law of cosines, even though cosine only shows up once in the formula. However, it applies to multiple cosines. I do want to point out to you, well, we'll get to it in a second. All right, so in the olden days, like just a few years ago, when a discus was thrown in a track and field competition, the referee would directly measure the distance using a tape measure, and that's probably how things are done here at the high school. So with super advanced technologies, lasers can be used to measure indirectly. So let's walk through to see how that works. So here we have what's called the discus pit, or the throwing pit, and there is the center of it. A person will stand anywhere in that pit to do a measure, to do the toss. And they can be within that, but they can't cross over the barrier there. So then they toss the disc, and we're only going to look two-dimensionally. We're not going to see it flying in the air. They toss it a certain distance, and then the disc lands. Well, somewhere over here, there is a little camera that pretty much can measure distance. It can measure the distance there, and then it can rotate and measure the distance there. So built in to this laser camera tech, it has 3 measurements that it can take. Number 1, it can find the distance here. We'll call this one A for no particular reason. So it can find the distance from itself to the center here, or it could just know it just because it's been entered, or it can find it by the person standing there, and it can measure that distance. Because the laser jumps there, bounces off, something like that. Next, it can also find this distance right here, which for now we'll call B. And it also knows this angle right here just because it does the rotation. If the camera itself is rotating, or using a beam of whatever, it knows how many degrees or how many radians it has here. So notice the situation in this diagram. If you recollect back from geometry days, There is no other triangle that can be formed if you have these three dimensions. Because by side, angle, side, this is the only triangle that will be formed. Okay, so using this information, and notice it's not necessarily a right triangle. We don't know if theta is a right triangle. So in that case, this distance here, which we'll call C, is able to be found. So, thus far, cosine, sine, anything in trigonometry that we've talked about is only applied to right triangles. However, using more advanced techniques, we can actually find out distances and angle measures without a right triangle. So here's what's called the law of cosines here. The law of cosines states this, that C measure, so this side C is opposite angle C here. I do want to point out that this is lowercase because it is a distance, it's a variable. This is uppercase, it is a location, it's a point, okay? So C squared here is equal to A squared plus B squared, which sounds very much like Pythagorean theorem. But to account for the non-right anglage, we're going to have to subtract 2 times AB times the cosine of this angle here. So this is how it is. This can only be used in a situation where we know side angle side. Remember, side angle side is the A is the included angle. The included angle. It's got to be the angle that's between the sides that you know. So for example, if you know side A and side C, you need to talk about angle B. If you know side B and C, you need to talk about angle A. The other option is if you know all the sides and you're looking for an angle. By the way, A, B, C are arbitrary here. A, B, C are arbitrary. Just move them around or change the letters as long as you're consistent. Notice that whatever side this is, A, B are the other ones. And whatever side this one is, this one here has to be opposite, the angle opposite. So if I was talking about angle B, then I'm going to say B squared is equal to A squared plus C squared. So this whole thing can change depending on your perspective. The letters can change. So we're only going to have you memorize the one, but you can switch all the letters around and still apply to others. So let's look at an example that's probably easiest for us to do. So the laser telescope that measures the distance to the center of a throwing circle, it measures it to be 30.1 meters. So it measures it to be 30.1 meters. And to the landed discus to be about 51. Since my scale is already off, I'm going to go ahead and adjust it a little bit. So I adjusted it and it said it's going to be 52, 51, something like that, out to here. But that's not the 51. This is the 51 right here, 0.02 meters. So the angle that the telescope rotated was 95 degrees. Again, my diagram is not very good, so I'm actually going to pause and fix it. All right, so now that I have all my information, my diagram's a little bit better. Notice that this angle is slightly larger than a right angle, so I did make that change. And I tried to make the red here longer than that. All right, so all we have to do is plug things in. Now, which one are we going to call C? Well, this distance here is the one that I'm looking for. So my distance squared is equal to the 51.02 squared plus the 30.1 squared. Now here's where we do the minus stuff. Minus the 2 times the 51.02 times the 30.1 times the cosine of 95 degrees. Before we just take all this and plug it into the calculator, tell your neighbor, what estimate do you give based on our diagram, which is not actually a bad diagram? How long do you expect D to be? All right, so we plugged that into the calculator, and I got my distance to be approximately 61.46 meters. So let's look at our final example here, and we're going to use the law of cosines to find an angle. So we're going to find the measure of the largest angle in this triangle ABC. Then we're going to find the measure of the middle angle. So I'll do the first one, and you'll do the second one. Now, in this context, what we know is side, side, side. So we don't know the angle. So I know A, B, and C. I just don't know the angle measure C. Okay, so we have to go back to our geometry days. How do we know where the largest angle is? So we do know that since 8 is the longest side, the angle opposite is in fact the largest angle. And the same goes true for the middle. 6 is the middlest side, which is not a word, and 5.3 is the shortest side, so angle A is the smallest. So we do know that B is the largest here. So as we are setting up the law of cosine, we just have to reconfigure. We're using this B instead of a C. Okay? So let's walk through it. I know that 8 squared is equal to, now I choose the other two, so I originally started with 8. Why? Because that's opposite the angle that we're dealing with. So I choose now the other two to represent the A and the C. Again, order does not matter because of the commutative property. Minus 2 times 6 times 5.3 times the cosine of capital B here. So as we work, I'm going to go ahead and multiply out a few things. 64 is equal to 36 plus 28.08. I could have done that at the same time. In fact, might as well. 36 plus 28.09. So that's 64. I can also multiply all this out right here. So minus 63.6 times the cosine of B. Now, as we're solving, I'm going to subtract the 64 from both sides. Then I'm going to divide by the 63.6. Then I have to undo cosine. So I subtract the 64. .09 from both sides. Okay, now we continue here. And this estimate right here is going to be, after we divide, is approximately 0.00141. And that's approximately equal to my cosine. The reason I said approximately at this point is because this number here is rounded. Now from here, we have to undo the cosine, and you have to make sure that your calculator is set to degrees. So when you do the inverse of cosine there and the inverse of cosine here, the cosine drops out, and you're left with the measure of angle B. And in this case, the measure of angle B is going to be approximately 89.9 degrees. And our diagram, which may or may not be drawn to scale, if we were to look at that, hey, that actually looks pretty much like a right angle. So that is going to be close. And now when you solve for the measure of angle C, which is the middle, angle, you'll end up with 48.6 degrees. And now what's nice from here is that all three angles, measure of angle A, angle C, and B, all sum to 180. So you don't have to use the law of cosines again to find out what this angle is. You just have to sum those and subtract from 180. So there you go, usage for the law of cosines, which looks very complicated, but once you get the hang of it, is quite fast.